I hope you guys had some big breakfast because today we're going to do some hardcore physics. In fact, I'm going to teach you all of calculus in about 12 minutes. Are you ready? Buckle up. Some of you may have taken calculus before. That's fine. If you have, talk to me in about 12 minutes and tell me I didn't teach you everything you ever knew in that entire semester. Here we go. So yesterday we looked at velocity versus time graphing. And we started with position versus time, then we went into velocity versus time. If I have a position versus time graph that looks like this, position, time, that looks like this, can you tell me what motion is actually happening right there? Well, we know that it's starting at the origin, and it's moving away from the origin, and it's moving at a constant rate. The velocity is the same because the slope is the same. And we said that the slope of a position versus time graph gives us the velocity. That was a key. So what would the velocity versus time graph look like? Velocity versus time. Well, we know that the velocity is positive because the slope is positive. We know it's moving away, and it's going to be constant the entire time. So it would actually look like that if the origin's right there. How do you get from position versus time to velocity versus time? Well, we know that we use the slope in order to get there. So the slope of a position versus time gives you velocity versus time. That actually in calculus is called the derivative. I know we don't need to use that word derivative, but it is actually what it is. And this right here, honestly, is the entire first semester of calculus. This is called, they would say that the velocity is the derivative of the position versus time. Now, technically, when we say that something's accelerating, we know that acceleration versus time means it's speeding up or slowing down. And in this case, it's not speeding up or slowing down at all. It's actually going at just a constant rate in acceleration that looks like this. So it would be 0. It's not accelerating. It's going at a constant rate. What's the slope of this? Well, the slope of velocity actually gives you acceleration. So to get from velocity to acceleration, we also use the slope. We could say that the slope of a velocity versus time gives us acceleration. Slope of position versus time gives us velocity. Slope of velocity versus time gives us acceleration. A calculus student would say that the acceleration is the second derivative of the position, but we don't need to worry about that kind of nomenclature because we are much better, we're in physics. Let's talk about equations here. We said that the velocity is equal to the change in position, or actually we should call it change in x, if we're looking in the x direction, over the change in time. We said it was the slope of this, the rise over the run, the rise being the change in x over the change in t. Slope is rise over run. And that's where we had our first kinematic equation. We actually called it average velocity over that given time period. What about the slope? If the slope of the velocity versus time gives us acceleration, I wonder if it's the same thing. So the slope of this, the acceleration, the slope of that would be the change in velocity over the change in time. The rise being the change in velocity here over the run, which is the change in time. This is actually another equation. Acceleration, in fact it's average acceleration, so I can put a line on there, is the change in velocity over the change in time. We are just added to our kinematic equations. So slope of this gives us this, slope of this gives us this. Let's take a look at another example. Position versus time, let's say it looks like this. If that's the case, the velocity versus time is going to be constant, but it's also going to be negative. So the velocity versus time is going to be down here. The acceleration versus time, again, this thing is not accelerating, it's going at a constant rate the whole time. It just happens to be moving towards the origin. So this is going to be also 0 again, looking at our equations or our graphs. Well, what happens if we are actually accelerating? What happens if our velocity is changing? Well, we got some weird things going on then. Let's start with our velocity versus time graph. Velocity versus time, let's take a look at something that looks like that. So if this is velocity versus time, this thing is accelerating. So the slope of that, acceleration versus time, is actually going to be, in this case, it's going to be constant, and it's going to be positive. So the slope of this, acceleration versus time, remember the slope goes from there to there. Since this has a positive slope, the acceleration is going to be positive. Now, what would the position versus time look like? That's a weird one. The position versus time. Well, here we have to start thinking about what's going on in our motion. We're starting out very, very slow. We're moving in the positive direction. So we're starting at 0 here, and we're gonna start our origin here. We're gonna end up out here. We're gonna end up away from it because it's positive. The velocity is positive. It's moving away. This would be negative. But it starts out slow. Now remember, the slope of position versus time gives us velocity. So if it starts out slow, we need to start with a very steady slope, and then it's going to get faster and faster and faster. So you can see that the slope here is steady, faster, 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 faster. The slope gets bigger. The slope of this gives us this. So if we actually pick a point here, let's say right here, I don't know how to find the slope of a curved line. That's actually really hard. But I can find the slope of a straight line using rise over run. So what we do is we actually draw a tangent line. So if I pick a point right here and I draw kind of a tangent line to that point, I can find the rise over run for that tangent line. That's going to give me this point right here on the graph. A tangent line up here is going to be much steeper with my rise over run. So up here, whatever that slope turns out to be, is going to be a much bigger number in velocity. So this velocity is getting bigger. The slope of the position versus time is also getting bigger. Remember, with position versus time, you want to look at what is the slope, and then the velocity versus time does that. Now in our class, we're only going to be looking at constant accelerations, which means in your acceleration versus graph, you're always going to have horizontal lines. It's either going to be 0 if it's a constant velocity, it's going to be positive if it actually is a positive acceleration, or negative if it's a negative acceleration. And then we can look at those other graphs as we go. Okay, I want to explain acceleration using this ball. Now, this ball is a great thing to think about when you're thinking about acceleration, even complicated things like this. A lot of things that we're going to do in physics is we're going to simplify it into a model. Now, if you can simplify it into something that's very easy to think about, it'll actually make your thought process a little easier. So a lot of the things we're going to do, I want you to just simplify it into what would happen to a point source or what would happen to this ball. So let's talk about the motion I want to look at in this ball. The first motion I want to look at is the ball falling. So looking something like that. If the ball falls down, what would the velocity versus time graph look like for that motion? Well, if it's falling down, it has a negative velocity. So all of the graph will be below the x-axis as a negative velocity. It starts up here. It actually starts at rest. So the initial velocity is 0. So it's going to be at 0, and then it's going to get faster and faster and faster as it goes down. We call this acceleration. It's accelerating. In fact, it's accelerating in the negative direction. It's going down, and it's speeding up. Okay? So the velocity versus time graph actually looks like this. And if you'll notice, the slope of the velocity versus time graph is going down. And we said that the slope of velocity versus time graph gives us our acceleration. So our acceleration is going to be constant, and it's going to be below the x-axis as a horizontal line. In fact, with gravity, it's constant all the time. It's negative 9.8. What about the position versus time graph? The position versus time graph, if we start up here and go down, it's going to start away from the origin. It's going to start at the top of the graph because it's actually going to end up near the floor. It's going to end up near the origin. So if that's the case, it's going to start up here, and then it's going to go slowly, and then faster, 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 faster as you go down, which means the The slope is going to be slow, steady, and then fast, 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 steeper, steeper, steeper as it goes down. So the position versus time graph is going to look like this. What about the motion where the ball is going up? So in its motion, the ball moving upwards. Let's think about that for a second. The ball's not falling down, the ball's going up. So if the ball is going up in the y direction, that means that it has a positive velocity. The velocity is positive. So the graph for velocity versus time is going to all be above the axis. It's going to start out fast. As it leaves my hand, the ball is going fast up. So it's going to have a high velocity, but then as it gets to the peak, the velocity is going to slow down because it's accelerating, or decelerating in this case. It's going to slow down and actually reach a zero velocity. And at zero velocity is going to be near the origin. So the graph is going to start up here, and it's going to end down here. This is what the graph for velocity versus time looks like for the ball going up. What's the slope of that graph? The slope of that graph is negative. And we said that the slope of velocity versus time gives us acceleration, right? So the acceleration is also going to be negative. Now, this is weird. This is weird. Because the ball is moving upwards. It has a positive velocity, but the acceleration is negative? That's odd. How can you be moving in one direction and accelerating in the other? Well, you can. And that's what makes acceleration so hard conceptually. For us to think about, how is it I can be moving one direction but accelerating in the other? So in this case, the ball is moving up, but it's accelerating down. Why? Because gravity's pulling it down, and gravity accelerates everything down towards the ground. Okay? What would the position versus time graph look like? Go ahead and see if you can sketch that for a second. We know that it's going to start at the origin. It's going to be going fast, and then it's going to be ending up slow. So down here, it's going to start here by the origin, and then it's going to go fast, really steep, and then it's going to gently slow down. This is what the position versus time graph looks like for this motion. So I want you to think about this for a second. When the ball goes up and down, let's combine these. The position versus graph is going to look like this. It's going to go up, and it's going to go down. It's going away and steep. It hits the peak where the actual slope is zero, and then it gets steady or faster and faster as it goes down. The velocity versus graph is going to have a positive velocity as it goes up, reach zero, and then have a negative velocity as it goes back down. The velocity versus graph is going to look like this. So the slope of the velocity versus graph gives us acceleration. So if we do the slope of this, it gives us acceleration. For this entire trip, up and down, the acceleration is negative. This acceleration graph doesn't really tell us much, right? It doesn't even tell us the direction the thing is going. We just know that it's accelerating downwards or in the negative direction. This is what makes acceleration so hard, is to think about you can move one direction but be accelerating the other. Try to wrap your mind around that, and let's take a look at some math. Okay, let me give you a situation. Let's say that I am walking at 2 meters per second for 3 seconds. Okay? If I'm walking 2 meters per second for 3 seconds, how far did I go? Well, that's pretty easy. 2 meters per second for 3 seconds. That gives me 6 meters. If I went 2 meters the first second, 4 meters by the second second, 6 meters by the third second. I can actually solve that using our equation. That velocity is change in position over change in time, or moving velocity over here, change in position is equal to average velocity times the change in time. So in that case, the change in position is going to equal my average velocity of 2 meters per second times 3 seconds, which gets me 6 meters. It's pretty easy to do in using some math. Let's look at what a graph of that would look like. A graph would look like this. So you've got velocity versus time, 2 meters per second, 1 meter per second, 2 meters per second, time, 1, 2, 3 seconds. Now, how would we solve that using this graph? Well, we're not going to use the slope, because the slope of velocity versus time gets us acceleration, right? So we don't want the slope. What did we really do there? We took velocity times time, got our change in position. Our change in position was average velocity times time. So in this graph, what am I actually doing? I'm taking this 2 meters times this 3 seconds right here. Look what I just did. I took 2 meters times 3 seconds. I found the area of that box. The area of that box gives me displacement. This is the displacement. The area of the box gives you displacement. This is another handy tool when looking at graphs. This allows us to go backwards, back up to position versus time. We know how to go from position versus time to velocity. We use the slope. We call that the derivative. Or velocity versus time to acceleration, we use the slope. We call that the derivative. But now we can go backwards. We can take the area underneath the graph to get back up here. Okay? That's actually in calculus is called the integral. And it's the second semester of calculus. And there you go. That's everything you ever need to know about calculus. So I just taught you all of calculus in like 12 minutes. But the idea here is the area under the graph allows you to go backwards. All right, so today's task is going to ask you to look at a whole bunch of different graphs and determine what the motion's like. You're going to be describing the motion in 3 different ways. You're going to be describing it in terms of words, if I give you a graph. You're going to be describing it in terms of graphing, if I give you words. Or you might want to describe things in terms of mathematics, taking some of those graphs and converting them into how far you went or slopes to give accelerations and velocities. Have fun. Good luck. Remember that the slope of a position versus time gives you velocity. The slope of velocity versus time gives you acceleration. And to work backwards, we use the area underneath the graph. The area underneath acceleration gives you velocity. The area underneath velocity gives you change in position. In doing the area and doing the integral, you can't go exactly backwards because you don't know the starting position, but at least you can get the shape of the graph. Have fun, good luck, and if you need anything, be sure that you're asking lots of questions either on the discussion boards or with me in class or through email. Good luck, and I'll see you soon.